All right, chapter 6 only has two sections, so we have already done 6.1, and I'm going to start in on 6.2 now. The topic in chapter 6 is discrete random variables, and so in this section we're going to talk about a specific kind of discrete random variable, which is called a binomial random variable. Okay. Here's a definition. An experiment is said to be a binomial experiment if four things happen. Item 1, the experiment is performed n times, where n is a fixed number. That's going to be key in one of the problems that I'll be doing shortly. Each repetition of the experiment is called a trial, and that's a term that you'll see. They'll be using trials. The n trials are independent. Remember that independence means that the occurrence of one trial, in this case, will not affect the outcome of the other trial. So for example, let's suppose that you flip a coin, and let's suppose that you flip a coin 10 times. N would be 10, and just because you get heads on the first flip, that has no effect over getting a heads on any of the other flips. Okay, so item 3 says that each trial can have only two possible outcomes. You're going to call it either a success or a failure. Okay, so for my coin flipping example, maybe it's a success if you flip heads and a failure if you flip tails. The notation that you'd find in the book, little p represents the probability of a success and little q represents the probability of a failure. Typically in these problems we'll be given the p value and we'll have to identify the q value in order to use a formula that I'll be showing you later. P is the probability of a success. To find the probability of a failure, you're going to take 1 minus p. That would be the complement rule. Item 4 says the probability of a success must remain the same for each trial. Okay, so if I go back to the coin flipping example, it's a 50% chance that you would get heads, right? And if you flip the coin again, it's still 50% chance of getting heads. It doesn't change to be 30% or something like that, okay? So that probability has to stay the same on every single trial. If all four of these things happen, we have a binomial experiment, and the random variable that we're using would be called a binomial random variable. And again, this is a specific kind of discrete random variable. Let's take a look at these problems here. Determine if each experiment is a binomial experiment. So we're just going to go through the 4 steps and check off each one that would be satisfied. So problem 10, a random sample of 30 cars in a used car lot is obtained and their mileages are recorded. So that would not be binomial because item 3 would fail. If you're just simply picking off mileage numbers on cars, that's not a yes, no, success, failure, 2-option type deal. Another way to look at it is mileage numbers are not even a discrete variable, right? Since you could have a mileage number of, 53,482.7 miles on it, you're not just limited to just whole number values. So it's not binomial because item 3 fails, but it's not binomial because it's not even discrete. And again, that's our focus, is on the discrete random variable. Problem 11, the number of people with blood type O negative based on a simple random sample of size 10 is recorded. According to the American Red Cross, 7% of people in the U.S. have blood type O negative. All right, so we'll go through our list here. N would be 10. N is usually the sample size in these problems. And you would have independent events going on. So just because one person has blood type O negative, that has no effect on another person's blood type. Okay. Item 3, there's only 2 outcomes. So either in this case, either the person is blood type O negative or not blood type O negative. Item 4, the probability of a success will remain the same on every single trial, since according to the American Red Cross, the stat here, 7% of people in the U.S. have blood type O negative. That's regardless of the individual. Anytime you identify an individual, there's always a 7% chance that they're blood type O negative. That wouldn't change from person to person. Okay. Problem 12, 3 cards are selected from a standard 52 card deck with replacement. That's key. The number of kings selected is recorded. So n in this problem would be 3. We're selecting 3 cards. And we would have independent events because this is being done with replacement. There's a 4 out of 52 probability that you would get a king, but that card's going back into the deck, so that probability will stay the same on the next selection. It's going to be 4 over 52. Item 4, of course, would be satisfied since the probability would stay the same on each trial. It's 4 out of 52. Item 3 is going to be satisfied since we only care about if the card is a king or not. Then it would be a success if it's a king, and it's a failure if it's not a king. So that would be a binomial experiment. Now again, keywords would be with replacement. If this is done without replacement, item 4 would fail, right? Because there's a 4 out of 52 probability of getting a king on the first try. 3 out of 51 would be the probability of having that next card be a king using the multiplication rule. So that would not be binomial in that case. Okay, problem 13. A baseball player who reaches base safely 30% of the time is allowed to bat until he reaches base safely for the third time. The number of at-bats is recorded. You're going to have two outcomes, right? Either he's going to get on base safely or not. You would have independent events, right? Since just because he gets on base safely one time, that has no effect on the next at-bat, like he could strike out or make an out some other way. The previous at-bats don't matter to the current at-bat. He's a 30% hitter, so every time he steps to the plate, he's got a 30% chance of reaching base safely. And so item 4 would be checked off there. And now item 1 is not going to hold up here because we don't know n in this problem. Like it could be that he never gets on base forevermore, okay? And we need him to reach base safely 3 times, and he can't get on base safely 1 time. So n would be not determined, making the whole thing not binomial. Okay, n, as I mentioned earlier, has to be a fixed number in a binomial experiment. Okay. Now there's a formula that we'll be using, the binomial probability formula, and I want you to kind of see where that's coming from in this problem 14. The Centers for Disease Control and Prevention reported that 25% of baby boys 6 to 8 months old in the U.S. weigh more than 20 pounds. Suppose that 6 baby boys who are 6 to 8 months old are studied. What is the probability that exactly 2 of them weigh more than 20 pounds? Okay, a couple things. First of all, since multiple baby boys are selected, we would know right away that we're going to use the multiplication rule, right? And now here's the thing. We want exactly 2 out of the 6 to weigh more than 20 pounds. The other 4, of course, would weigh less than 20 pounds, and there's a 75% chance that a baby boy in this age group would weigh less than 20 pounds. Okay, so here'd be my setup. I have to consider several different situations here. In this first part, you're looking at just the first 2 baby boys being more than 20 pounds. The other 4 are less than 20 pounds. Okay, but that's just one out of many scenarios to consider. Like you consider the first and the second being more than 20 pounds, and then the first and the third being more than 20 pounds, the first and the fourth being more than 20 pounds, the first and the fifth, the first and the sixth, okay, and then move on to the second and the third, the second and the fourth, the second and the fifth, etc. Okay, and so you'd have to look at basically every single situation of arranging the 2 who are going to be more than 20 pounds out of the 6. Now, when you compare all these, you're really doing the same thing 15 times, where you're taking 0.25 times 0.25 and then 0.75 times itself 4 times. So since you're really just doing the same thing 15 times, what I have here is how I would get my answer, which is 0.2966. All right, so the interpretation then would be to say that you have roughly about a 29.66% chance that exactly 2 out of the 6 would weigh more than 20 pounds. Now, we're not going to do the calculations like this. That would be brutal in most cases, but I do want you to kind of see where the formula comes from here. The coefficient 15 that I had right here is the number of ways of obtaining 2 successes in 6 trials. Okay, in general, the coefficient is represented by this symbol here. The way that we read that is n choose x, which means the number of ways of obtaining x successes in n trials. To find the probability of obtaining x successes in n trials of a binomial experiment, we're going to use the formula which is given below. Okay, now what I have written here is essentially this formula, okay, but we're going to go right to the formula rather than writing it all out. Okay, so this would be the formula to know for the section, and nearly all the problems are going to be where you're using this formula over and over and over again. X is binomial, so X is discrete, which means that X can only take on counting number values. Okay, X will never be more than n, since n represents the number of trials, and you can't select more than what's in front of you. Okay. Let's take a look at problem 15. It says, according to the American Lung Association, 90% of adult smokers started smoking before turning 21 years old. Suppose that 10 smokers 21 years old or older are randomly selected. Let the random variable x represent the number of smokers who started smoking before 21. Is this a binomial experiment? Yeah, it will be, since the 4 conditions are satisfied. N is 10. And you've got independent events. Just because one person started smoking before 21, that has no effect on when another person started smoking. We've got all smokers are in this group here. When they started has no effect over another person when they started. Okay, there are only 2 outcomes. Either they started before 21 or not. And the probability of a success will stay the same on every single trial because of this stat here. There's a according to the American Lung Association, 90% of smokers started before 21. So that's regardless of the smoker. You've always got a 90% chance that that person started before 21. The p-value, therefore, would be 0.9. Now, when we use this formula, p and q are going to be written in decimal form, although usually in these problems, the p-value will be given as a percentage. Okay. So now we're going to calculate some probabilities. Part B, we want to find the probability that exactly 8 of them started smoking before turning 21 years of age. That is 8 out of the 10. So I would go to this formula here. N is 10, P is 0.9, Q would be 0.1, since you're getting the Q value by taking 1 minus P. 1 minus 0.9 is 0.1. In other words, 10% of the population started after 21. Okay, and I need exactly 8 out of the 10 to have started before 21. So I'm filling in the numbers into the appropriate spots here. And now the next thing I want to do is compute 10 choose 8. How you would do that on the 8384 model is you're going to hit 10 and then hit math and then go over to PRB. And then we want number 3 where it says NCR, hit enter, and then 8, and it says 45. Okay. On the Inspire model, if you have that one, you're going to just hit calculate, and then we want to go to menu here, and then down to probability, and you'll want combinations. Hit enter, and it'll already set you up here. How you type this in would be 10, and then comma, let's see here, where's the comma button? Right there, okay, and then 8, and then hit enter, and 45. Right, so what that means is that there is 45 different ways to arrange 8 items out of the 10 items. Okay, and so that's how I'm getting that number there. And then I would take 0.9 to the 8th. 0.9 to the 8th would be 0.4305 if you round to 4 digits. 0.1 squared is 0.01. That's a rounded number, so I've used the approximation sign. At this point, I multiply these 3 numbers together, and I get 0.1937, as my answer. So what that means to us is that there's a 19.37 probability that we would have exactly 8 out of the 10 smokers starting before 21 years of age. Remember that because you're computing a probability, your answers are going to be in the range of 0 to 1. That will always happen. Part C, find the probability that at least 8 of them started smoking before 21 years of age. Okay, at least 8 means 8 or more. X is discrete, so when I say 8 or more, I'm only talking about counting numbers here. X could be 8 or 9 or 10. So I would need to compute these 3 probabilities where X is 8 or 9 or 10 and then add them together. So I've already got the setup for when X is 8. We did that earlier here. When X is 9, then you're going to want 10 choose 9 times 0.9 to the 9th, X is 9, times 0.1 to the 1st, that'd be 0.1. And then when X is 10, it's going to be 10 choose 10 times 0.9 to the 10th, X is 10, times 0.1 to the 0. 10 minus 10 is 0 for the power, okay? Like I said, we've already done this first part, so I just kind of rewritten that, what we had before. 10 choose 9 is 10. 0.9 to the 9th would be 0.3874, and I'm multiplying that by 0.1. 10 choose 10 is 1. Anytime you've got n choose n, that will always be 1, which should make sense. If you have n things in front of you and you select all of them, there's only one way that that could happen. Anything to the 0 power is also 1, not 0. So the only thing that we have to do here in this last part is figure out what is 0.9 to the 10th, and that is 0.3487 if you round to 4 digits. Okay. Here's the numbers that I'm getting in simplified form for these 3 probabilities, and when I add them together I get 0.9298. So there would be roughly about a 92.98% chance that at least 8 out of the 10 would have started smoking before turning 21 years of age. Part D, find the probability that fewer than 8 of them started smoking before 21. Okay, fewer than 8 means that X is less than 8. So X could be 7, 6, 5, 4, 3, 2, 1, or 0. Maybe nobody started before turning 21. That could happen. Now, rather than computing 8 individual probabilities, there's a faster way to do that, and that's to use the complement rule. Okay, if I take 1 minus the probability that X is greater than or equal to 8, I'll get my answer quicker. Be sure that you switch the sign there. And we've already computed that probability. That was what we had done in part C. So I guess to get the answer to part D, I'm just going to simply subtract that number from 1. So it looks like there's roughly a little bit more than a 7% chance that fewer than 8 would have started smoking before turning 21. That's unlikely to happen where you'd have fewer than 8, especially if 90% of the group started before turning 21. Okay. Now, if I were to have computed 8 probabilities, since there's 8 values that are less than 8, I would still get the same answer. That would happen. It's just I'm taking way too long to do the problem like that. So in general, when you see, look for that situation where you can use the complement rule if you have information already computed from earlier. Part E is the last one that we'll do here in this video. Find the probability that between 7 and 9 of them inclusive started smoking before turning 21 years of age. Inclusive means that you're including the endpoints. So I'm including those endpoints. And that's a key word, because if they didn't have that, being between 7 and 9 just means that X would be 8. So I have to look at this as I'm computing 3 probabilities and adding rather than just 1 probability. Now we've already got the last 2 probabilities computed from our work done earlier here. So the bulk of this calculation is just going to be in getting that first probability. When X is 7, it's going to be 10 choose 7 times 0.9 to the 7th times 0.1 to the 3rd. And by the way, the powers of P and Q, when you add them, will always equal N. Check it out here. 7 plus 3 is 10, 8 plus 2 is 10, 9 plus 1 is 10. That will always happen. When you add the powers of P and Q, you'll get N for the problem. All right, so now I need to simplify. 10 choose 7 is 120. 0.9 to the 7th, and then 0.1 cubed. I've got those numbers there. This is already been figured out, again, from our work done earlier, and right here. And so here's the 3 probabilities that you would get in simplified form. When you add them together, it looks like there's roughly about a 63.85% chance that between 7 and 9 of them inclusive would have started smoking before turning 21 years of age. Okay. And I'll stop the video right there.